next presenter, I would like to introduce June Slater, who will be presenting dangerous RPKI edge cases. This is June's first time presenting at NANOG, and it is a pleasure to have June here with us today. Welcome. There you go.
Thank you. Today, I'd like to take a look at RPKI ROV deployment. Specifically, I'd like to take a look at the edge cases that pop up, both in deployment itself and in the validation of that deployment. Before we get too far into this, today I am here on my own. This presentation does not represent the feelings, thoughts, expressions, etc. of my employer. Anything I talk about today is entirely mine. Blame me, please. I'd like to talk really about a discussion of trends. Any method that exists to measure ROV these days is going to be subject to implicit and often quite serious bias. This is certainly no exception to that. As a result, I don't really think that it's fair to talk about the who is doing something so much as the why something might be happening. What's actually a problem, and what might we be able to do about it? But what is RPKI, and what is this ROV thing? Well, let's say that you announce prefix A using your autonomous system X, and you announce this to your upstream autonomous system K. They, through the magic of the internet, pass it along to one of your customers' autonomous system J. One day, due to a misconfiguration in their router, or perhaps intentional acts, ASY announces prefix A as well. Because they've got a shorter path to ASJ, they end up winning the traffic, causing you to have what looks like an outage, and to your customers, a lack of service. Nobody's happy about this. Let's create a solution. That solution comes in the form of RPKI, Resource Public Key Infrastructure. Effectively, we can cryptographically sign certain pieces of sensitive routing information that allow us to figure out whether or not a given route has any chance of legitimacy. As it pertains to ROV, three things are typically contained in these signatures. The first is the specific ASN that we're interested in. Who is allowed to announce this prefix? The second is the prefix itself. And the third is the maximum amount that we will allow this prefix to be deaggregated to. If I have a /23, maybe I will let it go to a /24, but I'm not going to let it go past that. Assuming that this prefix is signed, and assuming that everyone happens to be validating, ASY's announcement can be recognized as wrong and can be swiftly dropped, ensuring that everyone stays happy, traffic keeps flowing as it should. Thus, ROV is really good at preventing a certain class of incident, anytime where the source AS changes. This happens a lot with fat finger announcements, but it's also happened historically for less innocent reasons. Occasionally, it'll happen due to deaggregation incidents. Perhaps most infamously, there's the AS7007 incident, where a full table was fed into a CIDR-incapable router, which understood this as Class Cs. These got sent back up to the internet, and we had a bit of an outage. But it also happens from time to time due to some BGP optimizers. It also happens due to direct intentional actions, such as in September of 2020, when some politically sensitive prefixes were briefly reacquired by a nation-state actor, presumably for the purposes of packet sniffing. Additionally, it's happened in April of 2018, when a large content delivery network's DNS prefixes were briefly reacquired for the purposes of cryptocurrency theft. Notably though, ROV does not prevent any instance where the source AS changes. Again, this can happen from time to time due to deaggregation announcements, but it tends to be rarer and it tends to only occur when a BGP optimizer is involved. Finally, it can happen due to direct intentional attempts at path manipulation, such as in November of 2018, when a regional cloud provider was knocked out because they had been hijacked by a nation state that was trying to censor them. Or in October of 2017, when an individual became the first IPv6 upstream to the Democratic People's Republic of Korea, simply by spoofing their ASN. All told though, perfection should not be the enemy of good. what ROV offers is still quite valuable. Just looking at the known list of incidents on Wikipedia, 85% of them would have been prevented by RPKI just by itself, assuming that everyone signed and that everyone validated. Most that wouldn't have been prevented directly by RPKI due to circumstances in how they were performed probably would have been far less consequential. And finally, it clears up the question of attribution. If I don't have to worry about fat finger announcements as much because there's not all this spoofing going on of just, hey, I accidentally happen to be in this path, all of a sudden the question of, hey, what's going on with that suspicious path becomes far less of a question. RPKI requires two different parts though, the actual signatures and the validation. While this is mainly aimed at looking at the validation, I think that briefly touching on the signatures is pretty important. NIST has a lovely portal for this, and if we look just at their frontline statistics, we see that 47.54% of the public v4 prefixes on the internet, at least as of 2 weeks ago, are currently signed and RPKI valid. This is really good. It's not the majority, certainly, but it's enough where we can look at this and say, okay, maybe the signatures are the less pressing issue now. Maybe it's the validation that's actually a problem. Unfortunately, validation is not something that's so trivial to look at. It occurs in the data plane, so we have to go to the data plane to actually measure this. To do so, we can take a relatively simple approach. Let's take an errand and a ripe allocated /24, announce it via a friendly local ISP who's willing to help with this, ping sweep the internet from those prefixes, see what comes back, invalidate the RPKI signature, wait for 24 hours, repeat the process, and see what the difference is. And if we do that, we get back a map that looks something like this, where hosts in black represent hosts that didn't come back, and hosts in blue represent hosts that did. This looks awesome. Everyone's validating. Mission accomplished, right? Well, not so much. What actually happened here is that my transit provider was more than happy to pass these along. But my transit provider's transit provider, not so happy. They filter on ROV good enough that this announcement didn't get anywhere. Right off the bat, this is a good result. It means that a widespread incident is not so trivial nowadays. But it also means that it's a lot harder to measure. We can't sit in a single position and trust that position to be accurate. So we need to step back and re-examine how we go about doing this. Let's change a few things. First off, let's announce these prefixes via an extremely large, extremely well-paired network, someone who will have more transit connections than perhaps me and my little colo. Additionally, let's try this with a different baseline. Instead of ping sweeping, let's see from the ripe atlas network who can actually reach out to us. This will constrain our results a little bit, but it'll also unlock tools like traceroute, where now I can see what path these probes are taking and what might have changed. Finally, let's take a look at DNS resolution and TLS issuance from these invalid authorities. Why? Well, RPKI, like any technology, has a Pareto point, that 80-20 point where we're getting a lot less benefit for the effort we're putting in. It's been hypothesized that if a few large service provider types, those being CDNs, public DNS services, large cloud hyperscalers, and a few large public ISPs, were to all start validating, we'd hit this point. And while I generally agree with this, there are a few very specific subset services that I think are particularly vulnerable, those being TLS and DNS. The reason I think this is purely history. We've seen these ones attacked before in previous intentional incidents. How might they play out in practice today? Stepping back with the new data set, we immediately see something very different. Again, black dots represent hosts that came back, blue dots represent hosts that did come back. Apologies, black is didn't. Just looking at this, this looks a lot closer to what we've seen coming out of both academia and what's been presented here at NANOG. But again, I'm not interested in the why. I'm interested in the how. How did these folks manage to make it back? Was it a default route, where these hosts are taking a full table, but they're also taking a default route from the transit provider? And as a result, regardless of whether or not they're filtering, they will reach out and they will still be able to reach the invalid simply because their transit provider isn't filtering. Is it peering, where regardless of what their upstream is doing, they themselves aren't filtering, and thus anything that comes over a peering session is still going to impact them? Or is it a single router in a single large transit provider that, for whatever reason, be it human or technical, isn't filtering on ROV? Thus, this provider is assumed to be safe, but any bad announcements that happen to get through that one router end up making it into the core and end up getting passed down to downstream users. Well, it turns out it's something of all of the above. If we take 100 random probes from each latency delta quartile, that is to say, the difference between the baseline and the subsequent invalid check, we see that very few of them, only 6 of those observed, appear to have what look like default routes. This is a conservative estimate since it's based on seeing a different next hop, and it also assumes that that next hop is implicitly going to be a non-IX IP and that it comes from some sort of a carrier or a ISP. And that being said, well, this is a conservative estimate. It fits in relatively well with the other 2 categories. 36% of the entire dataset, not just this constrained 100, ended up going through a single transit port with a single provider. That's quite substantial. It means that had that router been filtering, it's feasible that this would have been far less impactful. We would have seen far less people actually seeing a consequence of this. By far, though, the biggest impact comes from peering. Most probes that responded on the invalid didn't change their path at all. There was neither a difference in latency nor any particular change. It was a peering session, plain and simple. This suggests that peering really is the concern now. We've reached that point where the large networks are filtering to such a good degree where peering is really where the badness comes through. Earlier, though, I mentioned that we tested with both a RIPE and an ARIN prefix. Why do that? Well, it turns out that the ARIN root certificate, due to legal reasons, had restrictions placed on it prior to September of 2022. These restrictions effectively meant that any validation software could not directly have a secure by default configuration. After September of 2022, these restrictions were lifted, and it could be included by default. I was curious, did this impact anything? Did we see any visible change in deployment? Fortunately, we have a relatively reliable baseline. In 2018, Ben Cox did a ping sweep of the internet using the aforementioned ping sweep method, back when that was still relatively viable to do. 100,000 IPs in his dataset, or about 0.038% of the total sample, came back on the ARIN invalid, but did not return on the RIPE invalid, suggesting that they weren't checking against the ARIN root. In 2023, we see that the difference appears to have gotten worse. Why would that be? Well, it looks like this is actually a bias in the RIPE Atlas network. Just digging into it a little bit, there's one provider that's overrepresented in the dataset. In fact, it's not just one provider, it's one facility, and from what I can tell, it's actually just a single building. Talking with the folks who run this provider, it seems to be a known issue, so I've gone ahead and excluded them. And if we do that, we get a percentage that's a lot closer, 0.051%. This is close enough where I think it's relatively simple to say that this is probably just noise in the RIPE Atlas network. It certainly hasn't gotten any worse, but there's still a few holdouts who don't appear to be validating against the ARIN PAL. Those sensitive services, though, those are real interesting. Public DNS providers, the ones that advertise on DNSSEC and having really good privacy-sensitive caches, with one notable exception, generally failed to validate on ROV. In contrast, home ISPs or business ISPs, where those ISPs validated, generally did validate on ROV with their servers and thus were not able to reach a bad authority. This leads to a rather interesting scenario, where a user inside of an ISP that filters can still be impacted by an invalid. What can happen is if I'm an attacker, I simply hijack the authority for a given domain. Assuming that domain doesn't have DNSSEC, I can return an IP address that exists within a valid. Public DNS server will happily pick it up and pass it along to the user, who gets impacted all the same. Of course, there's still the protection of DNSSEC there. That doesn't exist for everything. Namely, it doesn't exist for TLS authorities, who are implicitly reliant on routing security to perform their validation. Unlike DNS, domain validation can also come in different forms, one of which is DNS, but it also encompasses things like email, like HTTP, and like TLS itself. I tested 12 different certificate authorities to see who would issue a certificate on the basis of some sort of an invalid. Only 2 were actually willing to. One issued it purely on the basis of an invalid DNS authority, and the other issued it both on the basis of an invalid DNS authority and on the basis of an invalid HTTP endpoint. Digging a little bit deeper, there's a little more to see here though. One particularly large authority behaved very weirdly compared to the baseline. The baseline involved checks from their infrastructure, but also checks from a very large public cloud provider. in the subsequent invalid check, I don't ever see that public cloud provider show up. I'm able to repeat this over a few tests, so it looks like it's some sort of a visibility check, something to make sure that multiple places are seeing the same thing. This is really good. It's good to have that diversity, but it suggests that this particular check was not intentionally done for the purposes of ROV, since we don't see it elsewhere. That is to say, it's safe, but it wasn't done that way intentionally. Additionally, the authority that issued on the basis of DNS by itself did so after a very long delay. The initial request in the baseline issued a certificate after only 22 seconds, whereas in the invalid, it did so after about an hour worth of waiting. That certificate showed up with a validator that was very weird compared to what we saw in the baseline, where the normal infrastructure existed in the place that this certificate authority is from. The fallback infrastructure came from Southeast Asia, with this host that very clearly wasn't validating. It's kind of the opposite of what we saw earlier. It's a fail unsafe configuration, where just because your main infrastructure wasn't able to verify, you still trusted this secondary set. Ultimately, though, this is all point-in-time data. Point-in-time data only does us so much good. We need to test this longer term. One of the best prefixes that are used for this is Cloudflare's isBGP-SafeYet prefix. It gives you an option to click a button and see whether or not your connection towards Cloudflare's edge happens to be verifying on the basis of ROV. It gives you this message, though, if it happens to fail the check, that encourages you to tweet at your ISP. This could foreseeably have unintended consequences. An ISP flooded with tweets encouraging them to deploy ROV all in rapid succession might see fit to manually block this prefix to buy themselves some time rather than immediately jumping into ROV, thus biasing this prefix's ability to accurately measure who's validating and who's not. Fortunately, we don't see this at any scale. The numbers between my test prefix and the Cloudflare test prefix are remarkably similar, especially given the difference in how they were announced. Digging even a little bit further, I see that there doesn't appear to be any major AS block that occurs that I can't attribute to noise from the aforementioned Aaron Tau. And digging even further, I don't see any AS blocking it in mass that isn't also unable to reach the aforementioned earlier test prefixes. Thus, I think it's fairly safe to say that the Cloudflare test prefix isn't blocked, at least not in any mass. This is really beneficial. The Ripe Atlas network actually does a persistent check towards the Cloudflare invalid test prefix. Like the map similar, black dots represent hosts that can't reach it, and the greener the dot, the lower the latency. This provides a really good view into peering, as Cloudflare operates a relatively well-peered network. But they're not the only ones, and like I mentioned earlier, any one perspective is going to lead to some bias. Fortunately, Ripe themselves have their own test prefix. It's not announced in quite the same way, it's got a very different set of peers and a very different set of transits, but it still provides a very good and unique view. With these two combined, along with several of the other public test prefixes that are out there, I think it's pretty safe to say that long-term tests against the known public test prefixes are not a particularly large risk, at least if you're not testing about a specific network. In summary, deployment is happening, and it's got real impact. At this point, filtering peers is probably more important than filtering upstreams. But if you're going to put the time in to validate peers, you might as well also validate upstreams, since there are still these edge cases out there. Routing security really needs to be considered inside of a threat model. If routing security could impact a service, perhaps the tools that are used to help ensure routing security, like ROV, should be included as potential warning flags. For instance, if I'm a TLS authority and the authority I'm about to issue a certificate on the basis of happens to be an invalid, maybe I shouldn't do that, or maybe I should queue some sort of a secondary check. Ongoing measurement can pretty safely use the public test prefixes without fear of widespread bias. And finally, while legal changes to the Aaron Tau have almost certainly simplified deployment, they haven't significantly impacted whether or not people are actually validating against the Aaron Tau. I would attribute this most, again, to the folks who have spent all the time to write validation software that is really good at having a secure by default posture, even when it wasn't feasible to do so easily. But I also have to thank Aaron for finally opening up the Tau so that it could be used by everyone without too many constraints. With that, if there are any questions, I will be happy to answer them. Alternatively, here's my email address. I'm happy to answer things there.
June, we got one.
Oh, we got one. Fantastic.
Sorry, a little slow on the uptake. It's Tony Tauber from Comcast. So how you said the percentage of people seeming not to use the Aaron towel is pretty low, but what was the actual number?
0.051%.
Yeah, but what was the actual?
Of the total number of probes that actually came back. Of the total data set, I believe it was somewhere in the 30s. I don't have the specific number off the top of my head. I will be happy to provide it to you here in just a few minutes.
Okay, thanks.
Anyone else?
Thank you, Tony. Thank you, Tony. Excellent. Thank you, June. That was wonderful.